Section 12.3, Double Integrals and Polar Coordinates, Video 2. I sort of lied at the end of the previous video when I said let's talk about how to convert an integral from rectangular coordinates to polar coordinates. Prior to doing that, there is one more thing that we need to discuss, and that's something called a polar rectangle. And I put quotes around the word rectangle because it doesn't look like a rectangle. Topologically speaking it is, but let's not worry about what that means. When you're in rectangular coordinates and you have a standard rectangle that you integrate over, because remember, a double integral is integrated over a region, and rectangles are the easiest region over which to integrate. You can define a rectangle by simply saying, let the x be between two values a and b, and let the y be between two values c and d. So if I were to set up a rectangular coordinate plane, and just mark A and B on the x-axis, C and D on the y-axis, then my x's have to stay between here, my y's have to stay between here, which means the region defined by these inequalities would be this rectangle. Nothing really revolutionary there. You should have seen rectangles by now. But what does a rectangular look like in polar coordinates? Well, if we define it the same way by saying the radius has to be in a certain range of values and the angle has to be in a certain range of values, what would this look like? Well, let's start with the angles. Remember in polar coordinates that the angle is defined by rotating in a counterclockwise direction from the positive x-axis. So let's just assume that this alpha and beta, for the sake of simplicity, are both positive, and let's say that alpha rotates this much. Okay, I thought I had a good juicy marker here. These markers have a very short shelf life. I'll switch out before the next video. But let's say that that's our angle alpha, and then we have another ray emanating up here, and that's our angle beta. So we're going to sweep out a region between these two rays, so it's going to be up here in this angle somewhere. Now, how do we define, or how do we use the radii, the R1 and the R2? Well, that's just how far you travel. So for example, let's say that the first radius is here and the second radius is over here. Then if we were to rotate a circle of that first radius and rotate a circle of that second radius, then the rectangle, quote unquote, would be this circular section right here, where every point on here has an angle between alpha and beta, and the distance traveled from the origins between R1 and R2. Now they don't always just look like little slivers like that. For example, you could have, and let's see if I can find a juicy black marker here. Oh well, we'll just not use a black marker. For example, let's say that we're going to do a polar double integral, and it's going to be over this half donut region, if you will. And let's say that the inner radius is 1 and the outer radius is 2. I really don't need to define the angles because it should be pretty evident from where this quote-unquote rectangle begins and ends. It almost looks like a rectangle somebody bent. The radii are going to be bound between 1 and 2. Every point on there is between 1 unit and 2 units away from the origin, or the pole, if you will. But what's the angle? Excuse me, what's the angle between? Well, starting at 0 radians, we do have some points over here, and this angle sweeps all the way over here, 180 degrees. Don't you use degrees in calculus? Pi radians. What if we had removed the middle of the donut and just shaded in this whole semicircle? What's the smaller radius now? The inner radius, 0. So when you're setting up a double integral in polar coordinates, you'll often have to determine your limits of integration. And if you have the region over which you're integrating, you need to think of it in terms of polar coordinates. What's the smallest and what's the greatest radius? And what's the angle that's being swept out from the beginning to the end?